Hello students, this is Dr. John, your physics and math professor, and today we have another friction problem. Here we have a 16 kilogram box sitting on this surface. The surface and the box together have a coefficient of friction of 0.42. Remember, the coefficient of friction is determined by both the box and by the surface that box might be sitting on. It's sort of a joint thing depending on the shape of each of them. And the box is being slid along with a constant velocity. Either it's being pushed or it's being pulled. I've drawn both the pushing person and the pulling person at the same time, but we're looking at them separately. What we want to do is we want to find out which of these is more efficient. In other words, which of these would require less force? Would it be less force to push or less force to pull? I've redrawn these things here because both of these are happening at 30 degrees to the horizon, just like this. 30 degrees up from the horizon in this way or in this way. And we want to know which is more efficient. And then we're going to have to explain this problem. I've written out the question for you there in a little bit more detail on the screen so you can see it and read it as well. And so what we're going to have to do is we're going to have to calculate the force needed to allow this box to slide at a constant velocity. To do that, let's just quickly review Newton's laws. Newton's laws, the first of Newton's laws is this: if something's moving at a constant velocity, like this box is, or it's standing still, which is also a constant velocity, then the forces are balanced. That is, the forces going to the right are the same as the forces going to the left. The forces going up, the same as the forces going down. There's a balance of forces, or there's no net force. The second one is if there is a net force, the acceleration of the box is going to be determined this way. It's the net force, that is, add up all the forces, subtracting ones going that way and add up ones going this way, and then that's going to be equal to the mass times acceleration. The higher the mass, the less the acceleration. And the third law is just a sort of a simple one, but it's hard to comprehend for most of us, and that is that forces come in pairs. If you push something, that thing pushes back. For every action, there's an equal and opposite reaction. So we're going to be using these three laws here, and we're going to start off by taking these different forces and adding all the other forces that there might be in this case as well. So obviously one of the forces is going to be the force of gravity, mg. Very straightforward. And secondly, because we have it sitting on a surface, we're going to have an upward force of the normal force. And the normal force in most cases is equal to the force of gravity, but in this case it's going to be slightly different because notice you're pushing at an angle or you're pulling at an angle. That's going to influence the normal force as well. And then of course, since we're sliding along the surface, we're going to have the always evil force of friction. The force of friction is going to be equal to the normal force times mu. And I'm just going to draw the arrow like this way down here. It doesn't matter exactly where you draw the arrows. I just put it over here so that I can write that in there clearly. Remember, the force of friction always opposes the motion. So if we're having motion in this direction or we're trying to push it in this direction, force of friction is going to try to resist that motion. So here's the 1, 2, 3, 4, 5 different forces that we have. I've tried to color code them a little bit so that you notice here the applied force. I've redrawn it over here. And this angle would be 30 degrees like this. And we've redrawn this one here as well, going down in blue. That's going to be 30 degrees as well. So the first thing that we're going to need to do is we're going to try to take this force B here and divide it into components. We want to know the component that's pushing in this direction. And obviously, look, there's a component pushing upward. Similarly here, there's a component pushing in this direction and a component pushing downward. We want to see if we can calculate those. If you remember your very simple definitions from trig, the sine of 30 degrees of this here is the opposite, Fy divided by Fb. The opposite divided by the hypotenuse. So that's the definition here. We can take the Fb and multiply that over here. And what we're going to get is we're going to get Fy is equal to Fb times the sine of 30. That's just taking this and moving it over there. And then we have Fy is equal to this. Now, of course, this here, very similarly, it's going to be, you can see it's going to be the cosine. So this is going to be Fb cosine of 30 because the cosine of this is the adjacent over the hypotenuse. And I did the same thing that I'm doing over here. Now, the same definitions apply down here to this thing over here. Of course, notice this is going downward, but other than that, the magnitude of these would be very similar to this. So I will use the same definitions over here, of course. It's just going to be a different force, Fa, but I could do the same thing over here, sine theta. So now I have those. For this diagram over here, we're going to need to take this diagram now and break it into x components and y components and make sure those equal to each other. First of all, let's take a look at this one here and realize there's going to be a component here, an x component here. This x component is going to be causing the acceleration in this direction. And realize that the force is going to be straight to the left. Those are the only forces going left and right for the purple one. I'm sort of ignoring this one for now. So that means this force here, this force right over here, so I'm going to call that Fb, cosine theta, so that's this one here, which is going to the right, this purple one over here, is going to have to be equal to what? That's going to have to be equal to the normal force times mu, because the forces to the left and the right have to be equal to each other since we're not accelerating. Remember, we talked about Newton's first law. So this here, this piece here to the right, FB cos theta, is going to have to exactly be equal to the normal force times mu. So that's the normal force times mu. And if we look at, so I'm going to do the purple one with this, I'm going to do the blue one here, different color with the other one. So if you consider that this thing over here, Fx over here, which I did here, Fa cosine theta, it's exactly the same as this. It's also going to have to be equal to the normal force times mu. So it doesn't matter if you're using Fa or Fb, I'm just going to write that in there, Fa cosine theta is also going to have to be equal to the normal force times mu. This is a different normal force than this. This is the normal force A, and this is the normal force for diagram B. So I just erased a few things here and I rewrote these things here. Fx, that's the force in this direction, is Fb cos theta, and Fy, which in this case is this force right here, is Fb sine theta. I just wrote those over here. We're going to need them. So here are one of the equations for the motion in this direction, in the x direction. We also are going to have an equation for the motion in the y direction. So let me use the purple one again because I'm going to be referring to this one here. So what are the different forces in that direction? Remember, we had a component here, a component of Fb that's going upward. What is that? That's this one right here. So the normal force, in that case, this one over here, has to be added to this component, which is Fb sine theta, and that's going to have to equal what? That's going to have to equal the force of gravity, which is equal to mg. That's very straightforward for this one. Let's do that for the blue one as well. I'm going to try to do these sort of at the same time. Notice in this case, we have a portion of your applied force that's going downward. So in that case, it's going to be slightly different. It's going to be the normal force. It's going to have to be equal to what? It's going to have to be equal to the two forces that are going downward. One is this thing here, which is Fa sine theta, and the other one is this one here, which is mg. So in the blue case here, we have the normal force going upward, this force, and this force going downward. Now we could rearrange this to look very similar to this, or we could arrange this one to look very similar to this. Notice to do that, we would just simply move this to this side, right? We would move, let's just keep it purple here, we would move this to this side, but it would become negative, right? So let's rewrite this here. Normal force is equal to mg minus Fb sine theta. And if I wanted to rewrite this, I would just switch these two around just so that they're the same as this. So it's going to be mg plus this. All right, I just rewrote this equation here. So we have these two equations now. We don't need this. We don't need any of this. Here we have our two different equations. This is equation 1 over here, and this is equation 2 over here. We can use these two equations because we have two unknowns. The Fa is unknown and the N is unknown. That's for the blue. And for the purple, again, the Fb and the N. Remember, these are two different things. This one here is an NA. This one here is a normal force B. So that's why I did them in different colors. I'm just trying to do it both at the same time. Otherwise, I have to do the whole thing, the blue, the whole thing, the purple. I just want to help you to see the parallels. These look identical. These look identical except for the minus sign. So what if we just use one equation, but I just draw the minus sign in there with my purple? So instead of putting this here, I'm just going to make this minus sign here for the purple. So this one here is plus, the minus sign is for the purple. It's for this one over here. So I can erase the purple here, and these are identical. Okay, let's plug this into here, the N into here. So I'm just going to leave this here, Fa cosine theta, but I'm going to divide both sides by mu here. So I'm going to take this mu and put it over here, just like that. Then I just have NA here and I have NA here. Then I can make this equation, what's left, equal to what's left over here, which is mg F sine theta. I'm just going to erase the A and the B here since we're going to be switching to A and the B depending on what we put here. So remember, we had the two different pluses and minus. I'm going to note those over here with blue and purple. And now we have something with a force here and a force here. Let's take all the forces to the left side and everything else to the right side. Give me a second to rearrange some things for you. Okay, I've rewritten some things here. I've left this right here. Notice I just put this mu underneath the cosine theta. And then I took this over here, the F sine theta, and moved it over here. But notice I reversed it. I made the blue minus and the purple plus because I'm taking this to the other side. So I just changed the sign of those. I left the mg on the right side like this. Now in this case here, what you can do is you can take an F out of both these, just like that. And we can put a bracket around there. There we go. Now we have this whole term here. We can take this whole term and divide this over here and have F equal to something. Okay, I've taken this, moved this up here. I just have the force on the left here is equal to this on the top, mg, and all of this. Cos theta over mu minus or plus sine theta. So this is my final equation now for the force. All I need to do is plug in the various different values. So here I've done a couple of calculations here for you. I've taken this here, which is the mass times g, and getting 156.8. Notice here we have two significant figures and 2 here. During your calculations, when you write things down, don't keep like 10 digits. Maybe keep 1 extra, 1 more than you have originally, or 2. Here I've kept 2 more, I've kept 4. On the bottom, I've done this calculation here and gotten 2.06. That's common for both problems. And then I have the minus and the plus. The minus is for the blue. The plus is for the purple, 0.5, which is the sine of 30. And I've done the final calculation of this, keeping the minus for the blue and the plus for the purple. Here would be the force you need to continue moving this at a constant velocity, 100.51. Or if we want to do this to 2 significant figures, this would be 1.0 times 10 to the 2, and this is 61.25, or 61 would be to 2 significant figures. I'm not worried about the significant figures right now as much as understanding these answers. Let's just write these in there and then discuss them really quickly. 100 for this one, and this other force is going to be 61. So here's the explanation you need to give. This force over here, you're pulling a little bit upward. So what you're actually doing is you're actually lifting the box a little bit from the ground. You're reducing the amount of apparent weight the box has on the ground. Hence, you're reducing the amount of force that the floor needs to push up at you, which is Newton's third law, which is reducing the normal force, hence reducing the friction. So by pulling upward like this, you're actually reducing the total friction. Hence, you don't need to have as much force in this direction to keep it moving in the same direction. By pushing like this down at 30 degrees, you're actually part of your component, your sine of 30 degrees component is pushing downward on the box, which is increasing the apparent weight and increasing the normal force, hence increasing the friction. So you're going to have more to push back against. So you're actually making your work harder by pushing than by pulling. So this is an old physics question. It's a very important one. I hope that you find it useful. I would rewind this tape to the beginning, look at the question, see if you can do it. Just try to do one side or do the other side. Don't do them both at once. I did them both at once just to show you what your teacher might do sometimes. And hopefully it wasn't too confusing. But if you like this video, like it, subscribe, and I will see you in the next video. Bye-bye.